logic homework, and I've been grading it. I did the math briefly yesterday. I've got 2,000 answers graded yesterday. By the time I answer all you guys' electronics math stuff, so I had to get creative, but I got a bunch graded. I haven't entered it into the computer yet, all of it, but I'll enter it in. So this logic gate here, and I may or may not have drawn the nose wrong, but oh, I need another line on this side, right? There we go. All right, so what would that be? An XOR gate, yeah. So looking at the back side, that concave makes it the OR, and the extra line makes it the exclusive. And the exclusive doesn't like pairs, so if I had a 1 and a 0, I'd get a 1 because it's a OR gate. If either one of them, or one or the other, are there, it'll give me a signal out the back side. But if I get a 1 and a 1 on this one, because we made it exclusive, it'd say, nope, we don't like that because we're exclusive. Now, the picture that we were like, is that an AND gate or an OR gate? There's a couple of them in there that give you the exclusive modifier, and then they put it on like this, where you go, okay, so you drew an AND gate on the front end. I'm like, yup. Well, I didn't draw it, but I'll have to fix it for next year. One of the big clues there is if it's exclusive, well, it can't be an AND gate, because an AND gate says if both of them are a 1, we get a 1. Well, it doesn't make logical sense to have an exclusive AND gate, right? But as you're going through the homework, if you haven't done it yet, unfortunately, we've got to slightly ignore the noses on ours. Normally, the OR gate would have a little bit more of a point on it, right? And some of the drawings we have don't. But be looking at the back side. AND gate is flat on the back side, where an OR gate is curved, and that's the pieces we're looking at. So anyway, getting those graded should be good. I'm gonna put them in the computer system and put them back in your boxes is the plan. So check your boxes today. I had somebody's, I can't remember whose it was, where I couldn't read some of the numbers, and instead of marking them wrong, and because I got 2,000 numbers to mark, I just put it back with a little note. I said, sorry, can't read this, try it again. Next time around, they just mark them wrong, because it takes too long to read 2,000 answers and then try to be like, is that a decimal? Can't tell if that's a 9 or a 5. I don't know. So that's where we're going with that. All right. We'll go with this next. So this whiteboard we said is not working, right? But just stepping you through for a moment how this is work. It'll be review for some of you, but it's our power box. So I plug it into the wall. I'm selecting by plugging these guys in or using jumper wires, DC down here, and this guy wants to be 24 volts. See if we can fire it up. Should be all set right. Ooh, light's already on. All right, these voltmeters I don't like, but Dean does. But they are kind of handy. Now the problem on this one is I go, man, where do I plug it in? I want to get ground here. Maybe I can grab it. Hey, that might work. For display purposes in the classroom, these are really handy because you guys don't all have to see what the voltmeter's reading, right? So if the light's on, 28 volts basically. How I do troubleshooting and the kind of simplest version for starting out, make sure all my switches are on. I always like to start on the simple side, so I would start on the wiring diagram and say, okay, well, red's power coming in. Make sure your meter's on, that'll get you every time, right? But even if you had a digital multimeter, you can just use an alligator clip it to the negative coming in and say, yup, I've got power coming in. And then I'm typically just gonna work through. So This particular one, we said our deploy is acting funny, it's not deploying. So we'll troubleshoot like we wanna see why is the deploy not working. So I'd say, yup, I've got 24 volts coming in. I'd come to my I terminal and say, yup, I got 24 volts at I. Next one in line is G. I got 24 volts at G. I would come down to my C terminal. Yup, I got 24 volts at C. And deploy normally is going to go between C and either D or H, depending on which way I put the switch. So I would go to D and say, what's going on? I do get voltage at D, so that means that the switch itself is working, right? When I switch it to the backside, but it doesn't deploy. So from there, we would say somewhere between D and 6, are we losing it? So I would double check at 6. Oh, I still get it at 6. Let's say I had it at D, but I went down to 6 and there was no voltage. Then you'd go, oh, that wire between D and 6 must be broken. And you could stop there, or you could grab a jumper wire and just go between D and 6 and see if the thing deploys, right? But I'm all the way down to 6. I still have power at 6. On this wiring diagram, that's pretty much all the further I can go. So I would say I've got something faulty on the inside of my lamp for that particular fault. Now, that's not listed on here, so use the other board, but you can go through the lamp faults, the rotate faults. So if you pick the other faults on there, if we get a backup, hopefully today I'm going to double check what fault numbers we're supposed to go with deploy, and either change the labs or just tell you, hey, on this fault number, use a deploy one. But so that's how I would just walk through. You start at the beginning of the wiring diagram and just walk through and see. Now a trick, and I think one of the faults in here somewhere, is they'll actually cut the ground wire. I'm gonna shut this off before I get myself. There's some solid state capacitors that take a little while to die on these. Every once in a while they'll give you a funky fault. But if we were drawing that wiring diagram up on the board, they just draw it as a negative and positive. The reality is essentially you got a battery hooked up, right? So that negative then goes through, I think it's terminal 1 is what we would call ground, and that goes down to our lamp body, we'll call it. And off the positive side is where we go through all our circuit breakers and blah, blah, blah. We'll say we go through our switch, through our terminal strip, to, I'm just gonna label it H, I don't know what it really is, to terminal, I don't know what it really is, I'm gonna say 4 at the moment, to our lamp. So there is basically a complete circuit. We don't know what's going on inside there because they didn't tell us. One of them has a wiring diagram on the back. The reality is it's not quite as simple as just, hey, it goes into it and I got a motor for deploy and I got a motor for undeploy and I got a light bulb for the light bulb. It's not quite that simple. There's actually a stack of relays inside there. So that's why we don't tell you what's on the inside. So the assumption is if this was the, let's say, deploy out terminal, we just want you to realize following the wiring diagram. If we connect it, if I put the wiring into our lamp box on deploy out, don't worry about what magic happens inside. And if you have power at that terminal, and it's not deploying out, you'd say, okay, it's a bad lamp assembly, send it in for repair. That's kind of what we're going with on this lab. But let's say we close this switch, we're assuming the lamp goes to deploy out, so I got my voltmeter. Instead of using 2 hands, I'm just gonna alligator clip 1 up to my negative here. So let's say we assume our wiring diagram is like this and everything should be working, and I go here and I've got 28 volts, and I go here and I got 28 volts, and I go here and I got 28 volts, and I go here and I got 28 volts, and I go here and I got 28 volts, but it's not deploying. What's a possibility beyond just a bad lamp? Yeah, we could have a broken wire over here, right? If we have a broken wire over here, and if that's broken, back to if there's no amp flow, if there's no amps going through our system, I would continue to have, and I'll draw it in just for the fun of it, I would continue to have that voltage pressure through my load all the way to wherever the broken wire is. I'll just draw it like that as broken. So if I come out the back side of the lamp and I still have 28 volts on what should be ground on the back side of the lamp, I go, oh, I must have a broken ground wire. So that's one fault you could have, is if your component, man, I got power at my component, but it's not working. You can always double check to make sure that the ground side is grounded. Now, a couple ways to do that. One is you can take your voltmeter and go from the voltmeter on the back or the ground side all the way to the ground and see if you get a voltage, because if it's broken, we would get one, right? So that's one way to do it. That's about the only way to do it. So that works. Now, could be a wire on an actual aircraft. That wire doesn't exist most of the time. On an actual aircraft, the battery's grounded, we'll call it bonded later on, and the component, the shell of the component itself is grounded. So the wire's not necessarily there to get broke, but there'll be a little wire that connects it to ground. Now what we can have happen, and it happens more often than we want to admit on old aircraft, is the component itself, where it's either mounted or whatever it's using for ground, it won't be well grounded. So it's essentially like having that broken ground wire. So if I were to go with my voltmeter just to the shell, if you will, the screws that mount this, so if I went from my voltmeter from the shell all the way up to my ground and I had voltage there, you'd go, whoa, that's really strange. I must not have a good ground, or my ground must be broken. That's one place, with all this rambling, that is one place that I will admit these style voltmeters are kind of nice, because if you use your little digital multimeter, these we say really don't have any amp draw that goes through them when you're checking for voltage, right? They're just a monitor, and they go, hey, do I have voltage or not? So sometimes, especially if it's a grounding problem, it's not a perfect break. Am I grounded? Am I not? Sometimes it's kind of a weak connection through a corroded component. You guys are learning about components. So if the component has, I'll put it fuzzy. I don't know how else to do this. If it's got a fuzzy ground there and you use a multimeter, you might say, no, I think I'm grounded, it seems to work. But if you use a voltmeter like this, where it actually takes a little bit of amp draw to light it up, if I were to take this one, for instance, and connect it to whether it's the ground wire or whatever I'm going to, and then go to ground, amp draw would actually have to flow through this meter, right, to light up the light bulb. And the corrosion might show up as, ooh, that's not a good connection. And instead of getting a nice bright light bulb, I might get no light bulb or just really dim. So I still don't use these, they're not my favorite, but that's one place that these things can be handy, is if you have a ground problem where it's, it's making a connection to where your multimeter is picking up the voltage, but it's not making it through a rough connection. Those can be handy. Dean's got stories of like tail lights on, I think it was like a Cessna 206, where the light won't light up. And the guy pulled the light off, and he's using his multimeter, and he's like, I've got voltage to this thing, I don't know what's going on, but it won't light up. But when he reconnects everything and puts it in line, he doesn't really have voltage. So he'd have voltage here, but when it's all connected, the voltage goes away. He's like, it's moving around, my voltages are moving. So if you use a meter like this, you can backtrack. So just some funny things that can happen, but making you aware of a little bit different style and how we do it. I saw a hand. Finney.
So, like if you suspect bad ground or like corrosion, you could do resistance too, couldn't you? If it has a high resistance.
You could, yeah. The hard part with bad grounds is you can sometimes get either different voltage or different reading when the component's trying to run versus if you're just doing a resistance test. And part of that is just, I don't want to say experience, but just kind of experience of, oh, this is really frustrating me. What's going on? You can even get to, maybe the corrosion is in a spot in this area, right? So when you it's in here and you have the component disconnected and you're just checking with a voltmeter and you go, I've got power to ground here, but when I put my component in, the power goes away. Because the component's trying to draw amperage, but this would be a high resistance, and Kirchhoff's law would say, well, the high resistance is going to eat up a bunch of our voltage drop, and we only got a little bit left out here. So that would be kind of a common place to look, and yeah, you could use an ohm meter, and you could check resistance all the way across that. We're expecting 0 or close to it. So that is a way to do it. Yes. But the other way to do it would be is if you suspect that you might have a wire or a connection issue, you can say, you know what, let me do it the other way around. If it's safe, depending on what the component is, you can cut your wire and you can say, you know what, let me just hook that right up to positive, see if my component functions. You'd eliminate all the wiring and say, oh yeah, the component functions, I don't have a gremlin inside my component. And then you get back to, okay, let me check close on all these, because maybe that switch contact from being deployed, maybe it's the contacts on the switch. Contacts on switches don't normally go bad, but when they do, they'll really give you grief, because every time you hit the switch, it like remakes contact. And it's like, it worked that time, not that time. It worked that time, kind of works that time. So as you get deeper in electrical, if you're actually troubleshooting, yeah, there's a whole world of little funny stuff that can pop up at you. But that's how I would use back to just work your way through the process. Start at the beginning and work your way through until you go, ooh, I don't have voltage anymore. I must have a cut wire. I must have a bad switch or something to that effect. All right, where's my PowerPoint? Today, we get to do a deeper dive into batteries. So we briefly talked about how batteries work. I say briefly. We didn't get real deep into the chemistry because I'm not a chemist, and that's part of why you have videos today. So a lead acid battery, we're going to talk about how the video is going to talk about how there's 2 plates, and basically there's a chemical formula on the inside that talks about, well, if we corrode or oxidize one, and then we essentially get 2 of our ions, and I'm already bad at explaining. So I'm going to let the video do it. I'm actually only going to let the video do it for about a minute. Oh, I bet I can't make it bigger. We'll leave it. I'm only going to let it go for a minute just to get you good and bored and put a couple of you to sleep. We'll see if it works. It might not do it on the PowerPoint because it's kind of sized to the slide. this is if you're into chemistry, it's pretty cool. Go back to my PowerPoint later and watch it yourself. But I'm going to let it go for about a minute and then stop.
Lead acid batteries are most commonly found in cars, in vehicles. Not electric cars, but common petrol or gasoline powered cars. The batteries used to start the engine, light the lights, heat the car, in some cases. Alright then, so there's two electrodes. There's a lead electrode and a lead 4 oxide electrode. And the electrolyte is sulfuric acid, which I've shown dissociated into protons and the sulfate ion. Now we're going to look at the discharge cycle when chemical energy is turned into electricity. So the sulfate ion goes towards the lead electrode, and see that 2- charge there, those 2 electrons? Well, they are going to come off and go through the wire. There's the half equation for this part of the cell. Lead and sulfate makes lead 2 sulfate and those 2 electrons. They pass through the wires, do some work, maybe light a light, and they go to the cathode. Now the reaction at the cathode is, well, something has to happen to those other parts of the electrolyte. 4 protons and the sulfate ion go over to that lead 4 oxide cathode and undergo that equation there. Some facts you do need to know about the lead acid battery. It's heavy, it's made of lead.
So we're going to get that in a little bit more detail later. But basically, there's a piece of occasionally where they take and go through the formula and say what's going on, and I realize unless you're really good at that, you're not going to memorize it. But you see the chemistry a little bit. The next slide excuse me, is the same thing, essentially. Click on the slide. The same thing, essentially, for a nickel cadmium. And it's a little bit more chemistry, a little more complicated. So we're only going to bore you for about a minute again, and then we'll move on with the class. But I just want to kind of give you an idea, it plants a seed, so that it's a reminder of what's actually going on inside the battery.
The nickel-cadmium or NiCad rechargeable battery. Well, here's the equation for the discharge part of the cycle. I'm pretty sure he won't be asked to learn this though. The cadmium gives off 2 electrons and that goes to the nickel 3 oxide hydroxide at the other electrode. Here are the 2 half equations, and try to find which one is losing electrons. Yes, the bottom one, the cadmium is losing electrons, throwing off electrons, so that must be the negative electrode, the one where electrons are being generated. And that's also oxidation is loss of electrons for that bottom equation, the negative electrode, which means that's the anode. So on the charging cycle, you just have to reverse those equations. And now electrons go from the nickel 2 hydroxide to the cadmium hydroxide as your battery is charging.
Yeah, so on the one hand you're like, what are you even showing us? And I'm like, yeah, I'm not going to get that. So long story short, when you're charging you go one way and it throws off 2 electrons. When you're using the power, it goes the other way. The one thing you should memorize, because the question will pop up, is they use the word anode and cathode a couple times, right? So if I draw yourself a battery, and we'll simplify it and just call it 1 lead plate here and 1 lead plate here. So this lead plate, we're going to say the chemical magic happens, and it's got extra electrons that's trying to give away to the other piece of lead. This one, you essentially say, oops, well, we actually said it backwards, didn't we? We're talking conventional theory, and then we're going back. So it's got positive charge. It wants to give to the other one. So we'll just go back to, if we have a positive terminal on our battery, talking conventional, That's going to be our anode, if you remember, anode. And the way I remember is it's right back to the diode drawing. So on a diode, the one with the A, and we would say, hey, if we want to make this work, we got to put positive electricity into there, is on the A side. So the anode is the positive. The negative side of this thing, or somebody said it looks like a K for cathode, even though we spell cathode with a C, is this side, so cathode. That's mostly what I want you to kind of pick up from the videos and just go, okay, there's some chemical formula going on that Case isn't going to memorize. He's not even going to try to teach me. But anode is positive, cathode is negative, and if I remember my diode drawing, or my transistor drawing for that matter, you got that. Because the anode cathode will pop up on questions. And it's good to have that one. All right, moving on. Here we go. This is the better video. It's going to be a little bit more boring stuff. Is the right slide? I think this is the one I want. Let me go one further. But it's worth watching. Where's my mouse?
This is nickel oxide hydroxide. Well, you have to give me an oxidation.
What happened here? Sorry. It's not. Oh, I see. That's the slide we were just on. Let's try that one. Here we go. Enjoy.
When we mix certain materials together, we can cause chemical reactions. This is when the atoms of one material interact with the atoms of another material. During this interaction, atoms will bond together or break apart. Electrons can also be released or captured by atoms during this reaction. When we talk about atoms, you'll usually hear the term ion used. An ion is an atom which has an unequal number of protons or electrons. An atom has a neutral charge when it has the same number of protons and electrons, because the protons are positively charged and the electrons are negatively charged, so they balance out. If the atom has more electrons than protons, then it's a negative ion. If the atom has more protons than electrons, then it's a positive ion. Rather than trying to understand this complex construction, we're going to simplify it down to this simple model of a cell with a single cathode and anode. In this cell, we have the electrolyte liquid, which is 1/3 sulfuric acid and 2/3 water. We have the positive electrode, which is the cathode. This is made from lead oxide. We then have the negative terminal, which is the anode. This is made from pure lead. When these materials are combined, we're going to get a small chemical reaction between the atoms. I'll show the atoms of these materials with these coloured spheres. The positive cathode terminal of lead oxide is going to react with the sulfate in the electrolyte. This will form a layer of lead sulfate on the cathode terminal. During this reaction, an oxygen ion is ejected from the cathode and into the electrolyte. Once in the electrolyte, these oxygen ions will combine with the hydrogen ions to form water. At the same time, the lead atoms on the anode are going to react with the sulfate ions in the electrolyte. This reaction will create a layer of lead sulfate around the electrode. During this reaction, 2 electrons are released and collected in the negative terminal. So now we have a buildup of electrons on the negative terminal. As electrons are negatively charged, this means we have a difference in charge across the 2 terminals, and we can measure this with a voltmeter or a multimeter. If you think about a magnet, the electrons are negatively charged, and so they repel each other. These are attracted to the positive terminal, which has less electrons. However, they can't reach this yet. So if we provide a path for the electrons, such as a wire, then the electrons will flow through this to get to the positive terminal. We can then place things such as a lamp in the way of these electrons and use them to do work such as illuminating the lamp. While the path exists, the chemical reaction continues. But this won't last forever. the chemicals required for the reaction will run out. The acid becomes diluted and weaker, and a buildup of lead sulfate coats both of the electrodes. This means the materials of the electrodes are becoming more similar, and so the chemical reaction becomes harder to achieve. But luckily, this chemical reaction can be reversed. So if we supply the battery with electricity from the alternator, we can start to reverse the reaction. The electrons enter the negative terminal and rejoin with the lead sulfate, releasing the sulfate into the electrolyte to leave just lead on the negative plate. The sulfate ions enter the electrolyte and combine with the hydrogen ions to release the oxygen ions, and so the electrolyte acid becomes stronger. The oxygen ions combine with the lead to create lead oxide, and this releases the sulfate back into the electrolyte, making it even more stronger. If we were to leave the battery to fully discharge for too long or too many times, it becomes very difficult to reverse the chemical reaction. Additionally, the sulfate layer could break away from the electrodes and accumulate at the bottom of the battery. This means it will no longer participate in the chemical reaction, so the battery needs to be repaired or replaced. So, when we look at the battery, this chemical reaction is occurring between every plate in every cell to provide the hundreds of amps of current to start the motor and also provide the voltage to power the lights, etc. This is then recharged by the alternator. Okay guys, that's it for this video, but to continue your learning then check out one of the videos on screen now and I'll catch you there for the next lesson. Don't forget to follow us on Facebook, Instagram, LinkedIn, as well as theengineeringmindset.com. When we mix certain material,
There. Alright, I'm gonna have to double check with Dean a minute. My math was a little interesting. So, the internet is disagreeing with what I told you, and it's agreeing with him. So if I'm sending electrons this way, what they're saying is they want the positive to be the cathode. The problem is, if I'm sending electrons that way, let's draw that back up, it would make sense. So I've done flipped it in my head, right? So let's say positive, negative, I'm sending, yeah, it's just backwards. It doesn't make sense. So I'm going to talk with Dean, we'll get back to you later in the day on that, why they reversed them on us. Because it just seems reversed, doesn't it? Because in a battery, we send electrons from this side to that side, and I'm going to have to figure that one out. Why? Maybe somebody can help us later too. Why do we reverse anode and cathode? Maybe it is they didn't invent the words until we switched to electron theory. No, that doesn't work either. So we'll check with Dean.
Well, a quick Google search looks like it's all the cathode is the negative.
I know, it's backwards of what the reality should be, isn't it? It might be, and what I'm finding when I have to ask Dean, is it might be that they switch it when you're charging versus when you're discharging, which would be frustrating, right? So when we charge the battery, the electrons are flowing the other direction, and they might have named it from when we're charging the battery, not discharging the battery, and I think that's what they're gonna get us with. So I'll review that for you, and my apologies ahead of time. Frustrating. All right. Two different styles of batteries we use. Now, lithium ions are round. You're never going to, well, I shouldn't say you're never going to see those. You're not going to see them much on small aircraft, and it's a pressurized container because the electrolyte is pressurized in lithium ion, so you're really not going to do much maintenance on them, and if you are, it's going to be really specific. So we basically don't cover much with lithium ion, other than it's a flammable or explosive battery that you got to be careful with. But so as far as maintaining goes, we deal with lead acid and we deal with NiCad or nickel cadmium. Lead acid, we'll use baking soda if we get any battery acid. So baking soda neutralizes the acid, so we'll pretty much always clean it with baking soda and then flush it off with water. So if you're using our tools, if you are checking battery acid in a battery and you accidentally spill some down the side of the battery or on the tray or on the table, when we go out there and I show you where the batteries are we'll use today, I'll show you the top left drawer has a bunch of baking soda in it, sodium bicarbonate, and you can use that to help clean up the battery acid and neutralize it, so the next guy that comes around and works on the bench doesn't get a little battery acid on his pants and then he's got holes in his pants. So we do want to clean that up. Lead acid ones, that's what we use. We obviously would not want to be careless or getting it too much around, let's say the top, to where it's going to go in the battery, because that would be a problem. So exterior of the battery, anything that acid spills on, that's where we're using it on. NiCad, because it's different chemicals, we'd mess up some stuff if we use baking soda, because chemically, that what we looked at, but not in detail, it's a little bit different. So they want you using ammonia or a boric acid. Now, we don't have NiCad batteries around here in our aircraft. I think that's a good blanket statement. And the general reason is because these gas off and the acids are a little bit different, you don't want to store, and you absolutely surely don't want to charge NiCad batteries in the same area as lead acid batteries. That question comes up all the time. It can damage the batteries because as they gas, they're giving off different chemicals, and the chemicals from one can damage the chemical from the other as they gas and ungas, if that's the right word, condense. So we stick with lead acid around here so that we can just say, hey, this is the battery section. This is where we charge our batteries, and we don't have to worry about the cross-contamination of lead acid and NiCad. So you're not going to see a lot of NiCad around here, and that's why our next video, when it comes up here in a couple minutes after break, is a little bit longer, gives you more details, is so you can be like, oh, okay, I see what's going on with the NiCads. But so there is those differences. Here's another one that's got the differences. Essentially, the big ones to remember are a lead acid battery. The charge can be checked by testing the acid with a hydrometer, and I'll show you how to do that in a few minutes here today. Where a NiCad, to for sure know how much charge or capacity, it can only really be checked by measuring it during a discharge with other equipment. The reason is they can get that voltage memory, or it can be have problems on the inside of it. So there's not a real great way to be 100% sure if that thing is all the way charged up or not without basically equipment that you can run the charge out of the battery and measure the amps for a certain amount of time. So this one we check with a hydrometer, that one you pull out and you check on the bench. Battery acid needs to be checked periodically. You notice that's on both of them. We talked last time when we were talking batteries about how the level of fluid in the NiCad changes a little bit different than the level of fluid in a lead acid. At the very end of a charging cycle is where they'll often say the gassing occurs in a NiCad, if you remember that. And the gassing is we're converting our acid, which is part water, we're converting that into a vapor because we discharge some hydrogen, if you remember. The oxygen goes on our plates. So as it's the most fully charged, our level can actually be a little bit lower on this one. That is not the case on our lead acid battery. So when you're checking, if you're checking battery acid levels, you gotta really know what kind of battery you're working on, obviously, to say, hey, how full should this be? And we're gonna cover that a little bit later on the lead acid. Just stretching. Only add when fully charged. This one is funny because it says only add when fully charged. I'm gonna say, make sure you read the instruction on there. It might give you a different level on fully charged versus not. I'm a little skeptical of who wrote this one here. Wondering, making sure he's got it right, but it's all gonna depend on what the manufacturer says on that one. Doesn't significantly change, level goes up and then back down when it's charged. Goes up, then down. So, I think I'm gonna have to do some adjustments on that slide. If acid spills, you would clean it with baking soda and rinse with water. That one, gas is at the end, and you might get a little bit of normal white, they call it moss or fuzz around the caps. It's that potassium carbonate at the vents. That part you can just clean up with water. If you actually had a spill, we're gonna clean it up with the boric acid or, whatever was on that last slide, is boric acid, ammonia, that's what it was, or ammonia. How often do you gotta check these things? That's a loaded question. Follow the battery manufacturer. I just put a lead acid one in an aircraft about a year ago, and the instructions in it said we had to check it at, it gave you a window of like 10 to 12 months, or a number of hours, but then it said, and every 6 months after that, and what it said to check it was, pull the battery out of the aircraft and actually drain it. When I say drain it, check the amp draw for an hour, and see if it's performing correctly, if it's at full capacity. That's normally the test we're gonna do for the battery over on this side, but it was a lead acid battery on this side. So, it's always follow the battery manufacturer. So if it's not the battery that came in the aircraft, so let's say you're working on one of Smat's planes, 3 Juliet Sierra, it's like a 1970s aircraft. What are the chances that you have the battery that came in it? Slim to none, right? So they probably put in a STC battery, because you don't just get to swap a battery out. If it's not the model battery that came in it, you gotta have an STC. Did you guys learn about STCs yet? Did you have regs class? Oh, coming up. STC means, this isn't what came in it, so you gotta get special permission to put that in the aircraft. You don't just get to put whatever in you want. And the STC pretty much will always say, follow the instructions that the manufacturer gives you. So if the manufacturer says, pull the battery out and test it on a bench, well, legally, you better pull that battery out and test it on the bench. Otherwise, technically, your aircraft is not being maintained, and it's illegal. Illegal things happen, but they shouldn't. Batteries are one of those areas where you go, oh man, and you're gonna love regs class. That's a lie. Because you'll find out there's so much stuff that you have to follow that's hard to follow. And that's why about half of being an aircraft mechanic is paperwork. It's tracking what you did and doing the paperwork to make sure you're following all the instructions, like battery instructions, that you should be. This one is just to repeat what I said so you don't have to hear it from me. Storing or servicing NiCad and lead acid batteries together increases the risk of cross-contamination, as the chemicals in each battery type can react with each other and cause hazardous conditions. So not only hazardous, it can wreck stuff. So we don't want to store them together, and that's why at SMAT we pretty much go, we'll just stick with lead acid then. Let me pause this for a second. I gotta double check where our brakes show up at. Tell you what, let's do a break here. This is a good spot, because I don't want to break the charging section up. So let's take a break. We'll make it a little bit shorter break. Come back at 5:02. We'll make the next break a little longer. check with the FAA which answer they like, right? That's frustrating. welcome back. I talked to Dean, and, well, let's see, he gave me the right answer, but it was one of those, that's what they call them. I couldn't come up with a real good reason on why it is reversed. We call the negative terminal the anode in a battery. He's like, yeah, I've been shown it. So I was thinking through it. I think part of it, and back to I'm not a chemist. Well, I'm going to go all the way back to if we have a magnet and we got a north-south, we always say the flux lines from a magnet, we say always go from north to south if we draw a direction, right? And then we go, well, unless you're inside the magnet, because it's essentially a complete circuit of flux. Inside the magnet, we say those flux lines go essentially from the south pole of the magnet to the north pole, so it does a reverse. I think when they're labeling batteries, they're kind of doing the same thing. So somebody can double check me on that to see if I'm crazy. But if we normally have in the electrical circuit where we would call the anode side and the cathode, because the flow outside of our battery is going that way. We like to say we have a complete circuit. If you were going to, like a magnet, draw it and finish it off, inside your battery, you would end up drawing it that way. Now, the reality is it's a chemical reaction going on, not a flow of electrons inside the battery. But in that chemical reaction, I think what they're doing is because to complete it, you flip it around, the anode side ends up being over there on the inside chemically. So I think if you understand the chemistry of what's going on, anode, cathode, that's where they get it. But all that to say, instead of saying case really confused us and get me fired, no, just kidding. Maybe it's an opportunity to say, okay, when we're talking about batteries, they flip the anode and the cathode around. When you're outside the battery, in the electrical world, the direction of flow is going to be how we always talked about it. The anode is the positive, power flows from the anode to the cathode. But inside the battery, the chemistry, they flip it around. I looked into, well, does it reverse when you're charging instead of discharging? And you could say when you're charging, it kind of changes, but the logic there starts to fall apart as well. So just reverse it if you have to answer a question. Speaking of charging, there's two different ways to charge a battery. We like to say this, we like to understand this, and then we go out to the chargers and you say, Case, which way am I using? And I go, well, it's a mix. But there are two distinct ways to charge a battery on paper. One is constant voltage battery charging. One is constant current battery charging. On constant voltage, we apply a set voltage to the battery and it charges it up. This is basically what you're doing in the practical world pretty much anytime you guys charge a battery. Is, let's say your battery is a 12 volt battery, you're going to put 14 volts on it, and the additional voltage that you're placing on the battery is forcing the charge, you can say the electrons if you want, but it's forcing it to do the chemical reaction. So that's what you normally do, that's what your car does, that's what airplanes do. Is if you've got a 12 volt battery, we're going to apply 14 volts to it, and that's going to charge our battery up. If you got a 24 volt battery, we're going to apply 28 volts. We're going to hold that voltage constant, and it's going to charge our battery up. So that means if we're holding the voltage constant, whatever current is flowing or we're pushing into the battery is just going to be a result of, well, it is what it is. So the idea would be if you got a dead battery, one that's not charged up, if you put a constant voltage to it, you'll get a really high amp draw when it's not charged because it's easier to force those electrons in. As it gets more and more charged up, it's going, I don't really need any more charge. I'm all charged up, and the amp draw is going to slow down. So if you've ever used a battery charger that's got a little indicator on there, when you first put it on, you'll notice it goes, there's a lot of amps, and as it gets charged up, it's like, we're not really doing much anymore. We're just kind of sitting here. So the amperage will change. That's basically what we do. Now, battery manufacturers will like to talk about a constant current charge. In a constant current charge, we'll get a device that will say, hey, Mr. Battery, you will take 1 amp, or you will take 10 amps of current, whether you like it or not. And it'll force it in. So that's one way to look at it. The flip side is the reality of most constant current battery chargers. The reality of most constant current battery chargers is that they'll say, you will take, if it's on 10 amp or set at 10 amps, it'll say, you will take 10 amps, but you know what, we're not going to give you more. So it's going to limit it so that we never have more than whatever the constant current is. That's why a lot of battery manufacturers are going to want this style, is instead of, let's say the battery healthily likes to accept a 10 amp charge, instead of having it take 40 amps for a couple minutes at the beginning, whoa, it says, no, we're going to limit it to 10 amps, and we're going to keep it 10 amps for either a certain time period or whatnot. So I just pulled 10 because you could do them at whatever the battery's rated at. So the issue with constant current battery charging is, as the capacity gets close to capacity, if you were to continue to force amps into that battery, number one, in order to do it, you're probably going to have to raise the voltage that you're pushing them in, right? But number two, we are probably going to overcharge this thing, get it hot, and damage the battery. So most battery chargers that you're going to encounter in the world are a combination of these two. They start out being a constant current in that you'll set it to, let's do a 10 amp charge, and it'll start charging the battery. If you truly applied a constant current of 28 volts or whatever, and the charger could handle it, you'd be overpowering probably both the charger and the battery, and the amp draw would just go off the chart and go, whoa, way too high. So the charger's going to say, we're going to try to do kind of a constant voltage, but we're going to limit our amps to whatever we set it at. So it'll start out at a limit. So if we were to draw that on, let's say, a chart over time, so time and amps, let's say it's a 10 amp again. So it's going to start out by saying 10 amps, but as the battery gets charged up, we get more towards the end of the charging cycle, the amp draw is going to fall off and say, I don't really need that kind of amperage. That's what's going to happen in reality. But if you're a battery manufacturer, if you have the proper equipment, you can do a straight constant current. Now, if you do straight constant current, a lot of times they'll only do it to about 80% charge, and then they'll be like, okay, let's switch, and they'll switch over to constant voltage. Make sense? Okay, trickle chargers are typically going to be let's call it constant voltage, and then they'll just limit the current going into them to a very low amp draw, and that's why we call it trickle, well, we're constant voltage, but we're going to throw a constant current factor in at a very low amp draw so that it just kind of trickles the voltage into there, and it can take a really long time to charge a battery with a trickle charger if it's dead. But they do a good job of maintaining the charge because they just hold the voltage at wherever we want it to be over a longer time. So this is sitting out there. Whoops. Elijah, what do you think? Yes. So back to like I was saying, so when you look through the FAA questions and they're like, put it on to constant voltage, this is both. It's similar. So you're gonna set the switch to 12 volts or 6 volts. This one says 6 volts, 6 amps, 12 volts, 2 amps, or 12 volts, 6 amps. So it's a combination. It's both of them. It's kind of a trick question. So this was one of the ones that got me as I was going through the program, because I'd go look at the battery chargers and I'm like, is this a constant voltage or is it a constant current? And the reality is most of these are both. So it's gonna say, I'm gonna hold the voltage at 6 volts, so that's constant voltage. It's actually gonna be probably 7.2 or something, right, just above it. And it's gonna say, I'm also gonna hold the amperage so it doesn't go above 6 amps. It's not holding it so it doesn't go below, but it's saying I'm not going to let it go above 6 amps. So if I get rid of our 6 volt one and just go over to these two settings, I've got 12 volts, 2 amps, and I've got 12 volts, 6 amps. So if I want to charge my battery up, basically, if I want it to charge faster, I'm going to want to pick the 6 amp setting because it's going to set the constant voltage at 12 volts. Reality is probably 14 volts. And it'll say, hey, I'll allow up to 6 amps to go into this battery. So it's that hybrid combination of both, where if I have a smaller battery, sometimes sending 6 amps into it is not good for the battery. So maybe we want the 2 amp setting where we say, you know what, I don't really care if it takes longer to charge this thing. Let's only allow 2 amps in. So that's why they're a hybrid. It was a trick question, and we don't have very many of, I'm gonna call it pure constant voltage or pure constant current. The generator, and I'll come to you in a sec, the generator on your aircraft or your car, you could say would be more of a pure constant voltage, but the limiting factor is somewhere in there, there's gonna be something that says, well, I'm not gonna let you charge more than 50 amps at a time. And the reason is gonna be the capacity of the actual generator won't be able to go past that. When we start talking about voltage regulation, we'll see where that comes into play. Ziegelbauer.
What happens to a battery if you do charge it beyond full on a constant current charge?
I think I have some slides where we kind of talk about it.
Okay.
And yeah, I've got some slides. We'll talk about it. Depends on the style battery, is one answer. The other one is with the chemistry in there, it's almost like a diode. Our diodes, what's the typical voltage in that depletion range? We say it's 0.7 volts, right? Well, the way the chemistry works and volts and all that interacts, there's a typical voltage on each cell of a battery, and I should have this number memorized, but I don't. It'll pop up a little later. If you try to put more voltage than what that chemically wants to see, that's where we start overheating, and we actually turn the plates and everything into a resistor, if you will, because we're putting more voltage than chemically it wants in, and we actually start heating the battery up. And we actually turn the battery into a heater. Well, we just made a heater out of something that's got acid and stuff in it. We don't really want to turn a battery into a heater, because if we keep that going, it can get real ugly, because we've got a heater that has its own energy stored in it, right? So that's the simple version is, if you overdo it, you turn it into a heater, which is not a good thing. All right, it would be the same question. This is the same kind of charger. And this one's got a nice needle, so if you set this thing to 50 amp, and start usually is, well, depends on it. I don't think they want you to start your car with it, but it'll swing all the way up there, and basically they're saying, hey, 50 amp or start, we're pretty much constant voltage at that point. But the reason it's 50 amp is this guy can't handle more than 50 amps. So it might have a limiting device in there that says, I can't do more than 50, that's what you get. But otherwise, we can set it to 10 amp, we can set it to 2 amp, and it's still constant voltage, but it limits it at that point. So it's hybrid. But we do want to look really close at the voltage output. So because these are constant voltage, we got to know what voltage we're setting it to. All right, this is the slide that kind of has to do with your question, Ziegelbauer, Nathan. NiCad has this warning especially. As a NiCad battery warms up, as it gets hot, the internal resistance goes down. And it can do, I call it a snowball effect, but I guess it'd be the opposite if we're getting hot. Is there an opposite of a snowball effect? The lava effect? As it gets hot, the resistance goes down, and then it gets hotter, and the resistance goes down more. Then it gets a little hotter yet, the resistance goes down even more. So if you set up a charger, especially if it was a constant current, but even a constant voltage, if it doesn't have an amperage limiting factor, you might set it up and be like, looks good, we're charging in the right range, and walk away. And then as that battery warms up, it can actually start charging faster, and it warms faster, and you can have a thermal runaway. So whether you're charging or discharging, you can have the same effect, charging or discharging. So we've done this math once before, and it's like right on the edge of where I even like doing it, because it messes with all the math we've been learning with electricity. But we're gonna do it anyway. So we got a battery, plus, minus, we're gonna call it a 24 volt battery. When we say 24 volt, the issue ends up being in an actual system, what we'll have when we're charging this battery is often about 27 volts, like if the alternator's running. If it's just sitting on the bench, yeah, maybe we're reading 24, 26 volts. We'll leave it at 24 for the moment. But let's say we run it over here, we hook it up to a heater or a light bulb, whatever you want it to be, and I put a switch in, and I come back. All right, so if I put my voltmeter on here with my switch open, let's say we read 24 volts. All right, so I'm reading 24 volts on my battery. The issue is when I close that switch, my battery voltage is going to drop a little bit. So it's going to change from 24 to something, and it depends on the capacity of our battery and all kinds of fun stuff like that. Let's say it drops to 22 volts. So now I'm running at 22 volts. So one of the issues there is if you really wanted to get specific with your math formulas and test some stuff, if this is open and you check the resistance with an ohm meter and say, hey, I've got 10 ohms of resistance. So we're gonna say 10 ohms, just for our math. If you check it at 10 ohms, and then you come over here and you check your battery when it's not running, and you say 24 volts, and then mathematically we should be able to do the math and say, hey, what amp draw are we gonna have? 24 volts divided by 10 ohms, I should have 2.4 amps, right? Well, there's a tricky little reality of our batteries aren't perfect. So the reality is, as soon as I close this switch, my battery voltage actually does drop a little bit. So it's going to drop to 22 volts. So when I'm actually working, I'm not seeing 24, I'm seeing 22. So what we would want to do to say what is my amp draw going to be is, well, okay, when it's operating, my battery's actually going to supply me my operating voltage. So if it's 22, So you'd be 2.2 amps. The reason I show you that little step is when the FAA asks some questions, they can throw you off a little bit with the math. You'd always want to do what your amperage is based on, well, obviously the voltage when the thing's operating, right? Not when it's just sitting at rest. That's only step one though. So I'm running 22 volts in my system. The step two of the math is they'll say, hey, what's the resistance, the internal resistance of my battery? And basically, step one can be just to say, hey, what's my amp draw in my system? And usually you're gonna measure this. If you're really gonna do this, you're not gonna calculate it, because we drew a nice resistor. The problem is with a light bulb, with a heater, as the temperature of that bad boy changes, our resistance actually changes. So on your little mock-up boards, if you measure a light bulb and get the resistance of it when it's cold, that's often not going to be the same resistance of what the light bulb is when it's hot. Because when it changes temperature, the resistance changes. So our cute little math we do, it doesn't always go straight into the real world, because if we change the temperature of a heater, we change the temperature of a light bulb, it can throw the numbers off a little bit. But assuming we actually measured this amp draw, so assuming that's measured, and this resistance, oh, you know what? We thought it was, we measured 2 amps. I'll leave it that way. We measured 2 amps, so we can calculate when our light bulb or heater's hot. Well, we actually have, let's see, 22 divided by 2. Anybody do that yet? 11? Oh, we actually have 11 ohms of resistance, because once our heater got hot, the resistance went up. So that's going to be the reality of more what happens, and it's probably going to be more drastic than that. So this one is measured. This one, what I have drawn now, is calculated. My actual calculated resistance. All right, so we could take this system and say, okay, I'm running it now. We know we have accurate numbers because it's a measured amp draw. It's a calculated resistance now that the thing's hot. Well, I lost 2 volts from where I was sitting, or I could say, I'm going to use the word static carefully, but static, right? I'm not moving electrons. So when I was static, I was at 24 volts, but when I'm operating, I'm at 22 volts. There's a 2 volt difference there. So I can use Ohm's law on that, and I can say, okay, 2 volts, 2 amps, what's my internal resistance of my battery? 2 divided by 2 would be 1 ohm. So they like to ask that question, and you get to, okay, the internal resistance of my battery is 1 ohm. All right, so back to kind of what Ziegelbauer was saying, is what happens if we overcharge it? You can do the math on, hey, I hook up instead of a light bulb to this battery, and now we're saying at rest it's 24 volts, but I'm going to hook up a charger that's outputting 28 volts. Well, I got a 4 volt difference, right, between what my battery kind of wants to be and what I'm at. So now I got a 4 volt resistance. I can kind of throw it in the same formula. Say I got a 4 volt. We found out I'm a 1 ohm resistance there. So how many amps would be going into this battery that I just came up with numbers? 4 divided by 1 is 4. So theoretically, at this state, that battery's going to want to see about a 4 amp charge. That's how much would go in if I threw a 28 volt charger on there. Now these numbers all, like I said, they start shifting around because that resistance and different stuff, as it warms, as it cools, it's going to change. But so that's all to get you to the point on a NiCad battery. As it warms up, the resistance goes down. So as it warms up and my resistance goes down, let's say I go I don't think it goes down this far, but let's say I go down to a half a volt. Half an ohm, excuse me. If I go down to a half an ohm, oh man, now I'm gonna go from I want 4 amps to go through to I want 8 amps to go through. And that's gonna warm it up even faster as it charges, and that's where you get that NiCad potential runaway snowball effect is as it warms up, the resistance goes down, and you could do that math the same way backwards. Let's say you got a hot NiCad battery. If all the numbers worked out, once the battery gets hot, it might be 23 volts, putting out your 2 amps. We got a half internal resistance, we're putting out more, and it just, yeah, we can heat up our battery from discharge as well. So, that's where the resistance comes in and why they want you to vaguely know about it. All right. Let me see here. So, this question came off a prepware type thing, and it said, let's say you have 2 batteries. That's a negative. I've got 2 batteries, plus, minus. And these are 12 volt batteries. But, oh man, I don't have a 12 volt charger because I don't know why I don't have a 12 volt charger. So they're saying, well, I got this 24 volt charger. Can I use this guy to charge them? Well, I can't charge one battery with a 12 volt charger, but if I put my 24 volt charger and then wire these guys in series, now I can charge them. So I can basically drop 12 volts across this battery, 12 volts across that battery. That gives me my 24 volts. Now the issue with that is the batteries have to be identical as far as the amperage for charging goes, because otherwise we might end up having that different internal resistance, right? And we might be putting too many volts. Maybe we put 14 volts into this one and not enough into that. So the way that question is phrased is, in a perfect world with, let's say, identical batteries, we could theoretically do this. In the real world, nobody's going to do this. They're going to get themselves a 12 volt charger. But theoretically, you could do that. Now, the other half of the question is, okay, let's say it's not so much a problem with, I got the wrong size charger, but maybe I got a 12 volt charger, and I only got one charger, but I got 2 batteries to charge. Can I do that? And you go, yeah, we could do that, plus minus. We can just put them in parallel. Because this is a constant voltage charger, we're going to have the same voltage across each in parallel. So I can do that. That's not a problem. And that works just fine. I could stack up a whole row of batteries and charge a whole bunch of them at once. This is what we might have to do when we get into our lab. If we don't have enough chargers, is we can just stack them up, constant voltage. If you've got a vehicle with more than one battery in it, well, this is what we're doing, right? You're just putting your batteries in parallel and charging them that way. That's how batteries are hooked up. So that's not a problem at all. It's the when they're in series, can we do series? So the reality is, the way the question is asked, if it was a pure constant amperage charger, 10 amp. It actually doesn't care what the volts are. It says, we're going to jam 10 amps through these wires whether you like it or not. And if it was doing that, you could hook up that pure constant amp charger to matching batteries. Number 1, they got to be the same. Number 2, what are we going to be worried about? If they're in series. Yeah, overcharging. Like once we get up to that 80%, just like if we had a constant amp charger on the right size, it's the voltage of this guy, it's going to fluctuate to hit whatever it wants to hit to hold 10 amps. So not only do we gotta make sure our batteries match, but we would also have to be monitoring this very close. The battery manufacturers will often tell you, hey, from no charge to full charge, it's gonna be 10 amps for 3 hours. So that's how you would use a constant amperage charger, is you'd set it up, you'd set a timer, you'd come back at 3 hours, and you'd take it off. But people forget, so we don't do that in the railroad. We don't. The battery manufacturers do. Some good aviation shops might. Different prepware question, and then I think we're almost to our break. This is talking about what each plate has when it's charged or not charged. And I'll admit, I don't have the numbers memorized. Normally NiCad, they're saying each plate in there has a 1.5 volt charge. Under constant current, let's see, make sure I'm reading this correct way, so I'm sure. Alright, when it's getting done charging, it's gonna be about 1.5 across each. And if you took it off the charger, it's gonna drop to 1.45. So what ends up happening is, well, if that battery's hot or not as hot, that internal resistance changes a little bit. So our 1.45-ish number is gonna move around a little bit. So this particular prepware question, they try to get you by saying, oh man, can I remember, what was that, how many volts per cell in a NiCad battery? And that particular prepware question, they like to just go, haha, we were just making sure you know that the voltage changes whether the battery's hot or not. So that's this particular prepware question. It depends on the temperature and the method used, because it'll move around. I've clipped this out and put NiCad is typically between 1.45 and 1.6 volts when you're charging it. When it's operating or sitting there, 1.2 is where we're at. So you do all that math, that's kind of like saying our 24 volt battery, we're gonna charge it at 28 volts, right? But just sitting there, it's 24. That's the same if you use that relationship, is where it moves around. All right, let's take a good 10-minute break. Come back at 22. Batteries. Does anybody want to challenge me and Mike with a little spike ball? Who said that?
I will take the rematch. Unless someone else wants to.
How about you two there?
I don't need to play either. Well, it's not good.
Oh, they don't want to get beat by us, Micah. Maybe I need a new teammate. All right, I got Yoder and Charlie. Does anybody want to play with me? Otherwise, I'll drag Micah back out. All right, Micah, it's you. We'll be back. No rush. this is photos I took of our lead acid battery. It says dry charged. They just mean they were shipping it to me without acid in it. So this is pretty typical Gill battery. It shows up with no acid in it. You have to add the battery acid to it. You fill it up to a certain level, then you tap it around, you give it some time for all the bubbles and stuff to work out, add a little bit more, charge it up, check the level, you might have to add a little bit more, and that's how it works. So how would I know if a battery like this is charged? We're not looking at the voltage output, we're looking at what is the specific gravity of the battery acid, because that'll tell us chemically how much chemicals did we convert to electricity and store in the battery versus where it was when we started. So that one kind of hurts my brain, because typically you'd want to grab like a voltmeter, right? I always see even Dean's Amazon battery kit, it's got a little meter in it that you can put across the battery, and it'll, essentially what it does is it says the voltage in the battery, right? Well, it doesn't work that way, because if you've got a battery over here, back to chemically, if it's half charged, if we've charged it to half its capacity, we still have a certain charge, a certain volt per plate. It's just our plates might only be loaded up. So theoretically, it's still going to say the same voltage. So if we just throw a voltmeter on there, if it's anything other than dead, we're going to get a voltage out. So the question is, how much chemical energy have we put in by oxidizing, or however you want to phrase it, on the anode and cathode rods inside the battery? And the only way to know that is to actually check the battery acid and say, well, what percentage is water, what percentage is battery acid? And if you're paying attention, I've said it a couple times, when they're charged up, they're 30% sulfuric acid. When they're totally discharged, they're water. So if you store one of these in the winter where it's cold, discharged, the water will freeze, it'll wreck the battery, and you're out of luck. So we want to leave them charged up, so it's 30% battery acid, and that's how it works. The theory there is, in the evaporation cycle, we don't lose battery acid on lead acid batteries. We only lose the water, the H2O. So if you ever go to check a battery and it's low on fluid, you don't add battery acid to it, because if you did that, you're going to mess with the chemical balance between the lead plates and the battery acid. So theoretically, the only thing to evaporate is water. So if we have to add anything to raise the level, we're going to add water to it. That's really important to kind of wrap your head around, because otherwise, you walk up to a battery in an aircraft and you pull the little vent cap off, and you look down in there with a flashlight and you go, oh, this thing's low. Well, it's battery acid. I better go find some battery acid to put in there. No, 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 no. Only the water evaporated. The other chemicals that are in the acid are still attached to plates and all kinds of funny stuff, right? So we're going to add water. They like to use the word distilled water. The word distilled just means we steamed it through a thing, so only the water evaporated. Any say materials, there's a word I'm looking for. Minerals, that's the other M word. Any minerals or anything other than water will not turn into a vapor and come out. So what we do is we turn our water that's got a bunch of junk into it into a vapor, and then recondense it into a jug, and then we'll use that jug to fill our battery, because we know we have pure H2O. We don't have H2O with contaminants in it. So when we refill a battery, we refill it with distilled water. Would we want to refill it with pure spring water? No, because pure spring water is going to have lots of good minerals for your body. We don't want those minerals in there. We want distilled water that's just H2O. So I'm going to click through some of the slides and just point out a couple things. It does say you can charge this in constant current. It also says you can do constant voltage. It'll say at the end of the charge, typically with constant voltage, you're gonna be down to less than a half an amp, less than 0.5 amps going into the battery. They say when you get to that point, you're pretty much charged up. If we left the charger on there, it might stay at 0.1 amps, like forever. And what's probably happening if that's going on? Ziegelbauer.
Sorry, say it again?
Say I got a battery and I leave my charger on, and I've got my fancy little amp meter, and I go, this thing's been on here for 10 days, but I still have 0.1 amps going into this thing. Are we like overcharging the battery, or what's more likely happening?
Undercharging?
Well, more likely, we're probably just turning the battery into a little bit of a heater. So if it's a tiny little amp draw, we're probably just pushing some voltage, so amperage, through the resistance of the battery and warming it up a little bit. But that said, not a good idea to just leave a battery on all the time and do that, because you could get to a point where, we are trying to overcharge the thing. It's not good for a battery to stay in that constant state of overcharge, because it's turning it into a heater. But yeah. All right. Continued airworthiness testing. That's the big line that you'll come across in regs class. And some of the slides will show up some of that stuff. This particular battery I put in was a G35, I believe. So as I'm clicking through these slides, I'm gonna kind of click over to G35. But airworthy limitations, it says at 800 plus or minus 50, so that means somewhere between 750 and 850 flight hours. It wants you to take it out and do a test, and or 11 plus or minus 1 month. So that would mean 10 to 12 months, somewhere between that 10 to 12 months. So that's a 12-month maximum, right? Whichever comes first, it wants you to take it out and do a capacity test. And right in the words it says, check for proper battery installation per STC, but the test is over here. Remove the battery from the aircraft. Charge it in compliance with the charging instructions, which you'll see a little bit later. Connect the fully charged battery to a capacity tester that incorporates a load resistance, so we're going to drain our battery, an amp meter, a voltmeter, and a timer, and discharge the battery at 1 hour capacity rate. Refer to this table. So on ours, the 1 hour rate is 23 amps. So they're actually saying put it on a test bench, and we're going to discharge this battery with a constant discharge of 23 amps, and we're going to see how long it lasts. We're going to hit the stopwatch and say, how long will this thing discharge at 23 amps? The battery is considered airworthy if it meets 80% of the 1 hour rating. And they do the math for you and basically say, hey, if this was a, let's go with 35 just for the fun of it. If it's a 35 amp hour battery and we're discharging it at 23 amps, theoretically it's going to need to last more than an hour, right? That's kind of the math they're doing. But we could run that math and say what's 35 divided by 23 times 60 minutes and see what it lasts. But long story short, this is the test the battery manufacturer says you should do. It's in their airworthiness limitations. If you don't do it, you're not following their instructions. Somebody cover up the camera and say, does this actually happen? Not very often. But it should happen, and be aware of it, because if anything ever happened and you were the last maintenance guy, you should be doing this. So anyway, you'll learn this kind of stuff in regs class of you have to follow the manufacturer's instructions. All right. There's the initial charging instructions. I threw this photo up here. It tries to give you kind of a cutaway, and it shows the filler caps, and then it also shows the top of the cells, or what they'd call the separator. So on the instructions, it's saying you shake up the electrolyte bottles, add electrolyte, And remember, this is the first charge, so we're adding the electrolyte. We're not adding water because this isn't charged up yet. We know chemically they gave me the right stuff. Install the vent caps and let the battery sit for 30 minutes. And it says you rock it back and forth a little bit. That allows any bubbles to come out. And it says sometimes the battery heats up because essentially all the chemical stuff's figuring out what it's doing and starting to charge itself up. After the soak time, you're making sure that the level looks good in each cell, making sure the bubbles came out right, and then you're going to add it to the top of the separators. And the separators are way down here. Common problem is people will look down in there and think that the split ring is the separator. And they'll add fluid all the way up to the split ring and go, oh, I'm at the right level. And then they put it on the charger, and we warm everything up, and it expands, and we got way too much battery acid. So you only do it to the top of the separators, connect it to a charger, begin the charging process, and it says you can use either way. You're probably going to do this on the constant voltage. They'll say the charge is complete when you get to a specific gravity between 1.275 and 1.295. So notice we're not looking at voltage. They don't say it's complete when the voltage is something. They don't say it's complete when the amperage drops below something. They say the voltage is complete when the specific gravity is the right level. And then after we check that, it says, okay, we'll do one last little adjustment with the electrolyte just below the bottom of the split rings. And when you look at them, you'll be able to see down in where there's a split ring. So it'll say add it to just below the bottom of the split ring. And they actually, it's kind of weird, they say do it while the battery's still charging. I'm like, oh, seems funny. I got electricity on there and I'm pouring stuff in, but that's what they like to say. And part of that is because when the battery stops charging, the electrolyte will cool down and it'll drop slightly. As the electrolyte cools, it gets a little bit smaller, and what they don't want you to do, why they say you do it while still charging, what they don't want you to do is walk up to a fully charged, cool battery, look down in there and go, oh, my level's a little bit low, let me add some water to it. They want you to do it when everything's warmed up and charged properly. If you walk up to the cold one afterwards when it's not charging, add it to the bottom of the split rings, well, the next time we charge this thing up and it warms up and it expands, we got too much battery acid and it spills out and it gets on your battery box and you got a big hassle. You'll learn how much of a hassle that is in airframe class when you all got to clean a battery box out. One of my least favorite labs that we do. All right, other than showing you how to check it, that all kind of makes sense. And this is a specific battery, a different manufacturer might have different instructions. But that's the instructions on this one. So I'm going to do a check. Normally, thinking through the safety things in my head in case Lyle watches the video. Normally, we don't even bring batteries into here because we don't want to spill acid on stuff and get it on our clothes, get it on our fingers, get it on everything else. So usually we'll even wear gloves, follow the instructions. They'll say you're probably going to want gloves on, you're probably going to want goggles on. I'm doing it in here on just one cell extremely carefully for you guys to get the point across. But you'll want to be careful because even just taking these off, if I was sloshing it around, I've got some battery acid on there, right? So wearing gloves, doing whatever, staying clean. But we'll show you how one works. They make these that are really big, huge ones, but basically they do the same thing. Inside here, there's 4 floating little balls that are different density. And basically, this guy doesn't give me a number. I should have went back to the other slide. A true battery charger, electrolyte tester, instead of giving you, are you on 1, 2, 3, or 4 balls, they will give you a number where it floats. And I should have brought one in. Maybe I'll grab one while the video is playing and bring it back in to show you that one. I just don't know where it's at. So what they did on these ones is they converted the number to how many balls are there. If all 4 balls are floating, basically they're saying we're at the 1.275 to 1.295. We're dense enough and my battery is charged. If only 2 of the balls are floating, I'm halfway between charged and discharged, which means I would be less dense, right? So I just take it off. Well, good thing I hopefully know that that's water, not acid. And the reason I say that is whenever you're done with these, you're gonna bring them over to the sink or you're gonna bring them somewhere and you're gonna flush it out really good with water because we don't want battery acid sitting in these things in the tray for the next guy to come grab and it erodes and corrodes and whatever else word you wanna use on all this stuff. So when you're done with these, you're gonna go rinse them out thoroughly with just water. So hopefully that was water. Hopefully the last guy to use it followed those instructions. I'm just doing a cup just in case I leak actual battery acid now. It doesn't go straight onto the table. So right now this particular one, and we're kind of waiting. Sometimes you gotta give them a tap because there might be air bubbles or stuff stuck in there. So I've got 2 balls at the top, and it looks like I got 2 balls floating at the bottom of there. Everybody basically seeing that? I got a green and a red on the bottom, I got a blue and a white on the top. So that tells me my density of this battery acid is somewhere between completely charged and discharged. So if this was completely charged, I would have all 4 floating up at the top. So right now, the red and the green are more dense than my fluid. As my fluid gets denser and denser, the red and the green are gonna go float up to the top. So that's basically what we got. It's really a simple thing. So when you're actually doing it, you pull the cap off, you check it, tap it around. Maybe you wanna do it twice just for the fun of it. But that's what we got going. I'll go rinse that off in a minute. This particular battery has, I think that's 12 cells. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I should probably be careful how much I tip it so you can see. But at 1 point something cells, actually these ones are tubes, it's lead acid, right? We're basically, this is a 12 volt or a 24 volt battery. So in an aircraft, you see 12 cells, 24 volts. So at lead acid, you're actually at about 2 volts per cell, where the NiCads are less, because it's a different chemical reaction. So this one is a 24 volt battery, and we could read it to find that out. But it's that chemical gives us basically 2 volts per cell on this, where a NiCad gives you less. So what I'm gonna end up doing with you guys is I was gonna assign you a partner, but we're gonna see what happens. You guys found partners fairly well last time. I'm gonna put this back on the backboard while the video's playing. And what we have on here is all your names. Number assigned is just gonna be, you can pick, I think I got them labeled 1 through 7 out on the workstations out there. And then, so that's the 7 on the table here. The C85 stand, I should have that memorized. I think that's grayish. Anyway, that's got a battery in it, so you can take the battery out of the test stand. That's another one that's available, so you can put C85. The big yellow power cart that we were using, I'm trying to remember, did you guys use the power cart yet? Okay. Last year and this year starts to blur on the years. That has 2 batteries in it, so I think you gotta take a side panel off and you can disconnect the batteries. That has 2 batteries in it. That should be enough if we go with 3 people per group. So basically, you're gonna come over here and you're gonna claim one. So you're gonna get your group. So on group here, you'll say, hey, we're group number, and what I'll do is I'm gonna say available group numbers. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just making it simple. So when your party gets together, let's say David, Micah, and Gavin want to be group 1. They'll X off group 1, put 111 next to their name, and then they'll pick one of the batteries. So we could even say, try to make this super easy. Battery available, and we could go 1, 2, 3, 4, 5, 6, 7, C85, power cart, and if you want to be an overachiever or learn more, get your money's worth here at SMAT, the 414 does have a battery in it. Is that in the wing? You can always ask Dean. You gotta take it out. That'd be more normal. So those are what's available. So if those three want to be group 1, they do group 111. Maybe they pick battery 3, and they'll pick 3. That makes sense for this for y'all? So I'm gonna let you assign yourself. If you don't get assigned by Monday, so if I don't see a number assigned to your name on Monday, I will finish it off and do it for you. So if you're it's not antisocial, but if you're not overly social like me, just don't put a number and don't find a partner, and I'll work it out for you. We'll get it worked out. So this particular lab is not that complicated. There's questions you'll do online. It's kind of split into 2 parts. So there's a Moodle part of Lab 19, and then there's a second part of Lab 19. I printed off like 10 copies. Oh, actually, I did that just right on accident. I printed off like 10 copies of what you're gonna do, but I'm gonna show you how to deal with the Moodle the way it's designed to be dealt with. Because it might be easiest to just turn this into me, and I would accept that. Part of me says, I don't know if I want my computer out there by all the battery acid and stuff while I'm testing it, right? So number 1, you could just write the numbers on there. Some of you guys don't mind putting your computers that close. I don't like it. Switch to this. There we are. Alright. Whoa. I dragged the wrong thing. I want that one. I want this one. Still figuring out computers. Let's try that. Alright. So there's my Moodle page. I think I'm an instructor though, and I don't want to be an instructor. Switch to student. Alright, this should be the same view you have. So you could go find your lab down here, or you could come over here and find the lab. I usually go on the left side. Here's the Moodle one that you guys have to do. Don't judge me, I didn't put that in. But you got these different questions on Moodle. If we go to the second one, here's how they want you to do it. It says, this practical project for 14019, I'll assign you in groups if you don't assign yourself. And same thing with the battery. If you don't assign yourself, I'll assign you one. So these instructions are going to be very, very similar for a bunch of Moodle labs through the year, especially Ryan's classes. I don't think you had any that go like this. You can read it on your own, but basically, you're going to hit the Add Submission button, and then it's going to give you this section. This is the instructions for it, and you're not allowed to type on the instructions because that would be weird, right? So what you'll do is you'll come over and get your mouse in just the right spot, highlight it all, right-click it, copy it, and then in the Add Submission section where it says Online Text, I'll go down and right-click again, paste, and now I have everything that was in the instruction section there, down in here, and this part I can type it. So battery fluid level, let's say it was below normal level, and I can check with my hydrometer and say, now unfortunately we're not going to have a number like a 1.2, right? We're going to have something like, I have 2 floaters, and I would go check each cell and say how many floaters did I have in each cell all the way through. I'd check the voltage, Then we're gonna put it on a battery charger, the correct one, 12 or 24 volt. Now here's the thing, we only have like 3 or 4 of them out there. Now a fun little thing is I would do this with Dean, just so he would smoke a battery charger. He's gonna be the guy that fixes it. We had, I thought, 2 24 volt ones, and about 7 of the batteries are 24 volt batteries. We got a ton of 12 volt chargers, like 6 of them. So Dean is saying, and I agree with him in theory, that if we take a 12 volt battery charger with a plus lead and a minus lead, and we take another 12 volt battery charger with a plus lead and a minus lead, if we run that minus to this plus, and then run this minus to our actual battery minus, and that plus to our battery plus, we have the correct 24 voltage now, right? Because Kirchhoff would say, in series we're stacking it. So basically we said, yeah, we can do that if we can't figure out who stole our 28 volt battery charger. I'm thinking if it's the first time I'm doing this, I'm gonna do it with Dean standing there, just in case the smoke comes out. He can help us put the smoke back in. But theoretically this works. Anyway, we'll be out there, we'll work with it. I have said before, and it never happens, but I recommend it all year, and maybe by the end of the year some of you guys will listen. I would recommend grabbing a sheet of paper and putting it on the battery charger with tape in your name that says, Sydney is using this charger with your phone number and the date. And that way, if somebody walks up tomorrow morning and says, who's using this? This thing's been charging for a day or 2. I'll just take it. Well, they know that Sydney's the one that's gonna come hunt them down. So if Sydney's name's on it, I'm probably not gonna steal her stuff. But the reality is, just so you know who's using it, it's not just the battery chargers. We've got, what, a week and a half, and you're not gonna have to charge them for multiple days. So you're gonna do the first part of this, you'll get it set up, and then you're probably gonna be waiting in line for a day or 2, depending on who you are, to get your battery on a charger and get it charging. Because after you charge it, you're gonna double check the fluid level. You're gonna go back in the hydrometer and say, yeah, and hopefully, you go do the little test, and oh, sure enough, I got 4 floating balls now. This battery works great. Now, if our battery is no good, we might not ever get to where all 4 balls are floating because it might just be a bad battery. But that is what we're checking for, and you get a voltage reading on the end. So I would recommend a piece of paper with your name when you're using the charger. That way we know who to hunt you down. And I like a date on this particular one as well, just so we go, when did they put that on there? And the instructors can hunt you down. Okay, so questions on the lab, on Moodle, how you do it, on how you're turning it in. After the video, I'll have this back there, so that's where you'll find it. Okay, that's what I like to hear. Let me get this back over. Am I right? I'm over to the right. All right. And the page, this comes back up. Current slide. Okay. This is a, I think, 15-minute video, 13-minute video on lead acid batteries. Then we're going to take a pretty good break, and then we're going to have a 20-minute video on NiCads, and then that's pretty much what I got for you for the day. So we'll be out of here by 9:45, somewhere in there. You don't have to take notes, but they'll reiterate some stuff, and it's just really good to see what they got going on here. Where'd it go? Where's my mouse?
The following precautions should be observed when handling lead-acid batteries. Warning: battery electrolyte will burn the skin and destroy clothing. When working with batteries or electrolyte, wear appropriate clothing and equipment. If electrolyte is splashed and spilled on the body or clothing, flush with cool, clear water. Do not wear finger rings when working with batteries. Do not use flame or spark-producing devices in the area where batteries are kept or serviced. No smoking. Refer to the Materials Safety Data Sheet and the Guild Service Manual for detailed safety precautions. Gill has been manufacturing quality batteries since 1920. Today, Teledyne's Gill aircraft battery is the most advanced lead-acid battery in the world, storing 45% more cranking or spooling power than could be packed into comparable batteries of earlier years. But to obtain this sort of performance over a long period of time requires carefully preparing the battery for service and faithfully maintaining throughout its life. The most critical time in the life of a Gill lead-acid battery is its wet down and initial charging. Although the wet down alone will bring the battery up to 70 to 75% of its full charge, using the battery without an initial charge will reduce both the performance and the useful lifespan of that battery. Always fully charge the battery before putting it into service. Here's how you wet down and charge the new Gill battery. Unpack the battery. Use handles or lift the body of the battery. Never lift a Gill battery by its vent tubes or Elcon connector. Inspect the battery to determine that there has been no shipping or handling damage. Make sure that you have the correct electrolyte. That is, electrolyte having a specific gravity of 1285. Electrolytes of other concentrations will seriously reduce the cranking and emergency power of the battery, especially at temperature extremes. Remove the storage seals. Then add enough electrolyte to each cell to just cover the separators. Be careful not to spill the liquid on the top of the battery. A film of electrolyte on the battery top can discharge the battery in a short period of time. Do not underestimate the importance of keeping the top of the battery clean. After electrolyte has been added to each cell, install the vent caps and let the battery sit for 1 hour. During that hour, occasionally rock the battery from side to side to release any trapped air. Check each cell, and if the electrolyte level has fallen below the top of the separators, add electrolyte to restore the initial level. Be sure to replace the vent caps before charging the battery. If vent caps are not installed, the top of the battery may become sprayed with electrolyte, which will cause the battery to self-discharge unless the battery is thoroughly cleaned. If possible, charge the battery using a constant current charger, which does a faster, more efficient job than a constant voltage charger. Teledyne can supply this type of charger. Be sure that you adjust the charge rate to that specified in the instructions packed with the new battery or in the Gill service manual. Never attempt to speed the charging by using a higher than specified current. This could permanently damage the battery. While charging, keep cell temperatures below 115 degrees Fahrenheit. Using a constant current charger, it will take from 18 to 24 hours to fully charge the battery. If a constant voltage charger is used, it could take twice as long. After the first hour of charging, check the electrolyte level in each cell. The level should have risen just to the bottom of the split ring. If the level is lower, add electrolyte. If electrolyte appears above that level, remove the excess with a syringe. Be sure to replace the vent caps. Clean up and neutralize any spilled electrolyte. When using a constant current charger, you will know that the battery is fully charged when the voltage measured across the battery has not risen for at least 2 hours. A small hydrometer, such as the Gill FR1, is the best tool for measuring the state of charge. An automotive or industrial hydrometer may not be able to gather enough electrolyte to provide an accurate reading. The Gill hydrometer indicates a range of specific gravity from 1100 to 1300. A fully charged Gill battery will have shown a specific gravity of 1285 to 1300 for 3 consecutive hours. Be sure to read the hydrometer at the electrolyte's lowest level, disregarding the surface curvature. Before disconnecting the fully charged battery from the charger, again check electrolyte levels and add or remove electrolyte, if necessary, to maintain the level just at the bottom of the split rings. After you remove the battery from the charger, neutralize any spillage on the top of the battery. Be sure that vent caps are on tight, because just a small quantity of baking soda in a cell will significantly reduce its power. Ordinary baking soda and water is the best neutralizer. Wash the battery top thoroughly with clean water and dry the entire battery before installing it or putting it away. To test a battery for traces of spilled electrolyte, connect the negative lead of a voltmeter to the negative battery terminal and run the positive probe over the battery top. Any voltage indicates a current drain between cells or between cells and a terminal, which will discharge the battery in a short period of time. Cleaning and neutralizing the battery will eliminate this problem. Before installing the battery in the aircraft, check electrical connectors for corrosion and good contact surfaces. They should be checked for pitting and contact of mating surfaces. Check the final installation to make sure that vent hoses are secure and are not kinked. The use of a sump jar is recommended in the battery vent system. Different styles are available from your Gill distributor. After the battery is installed, check the aircraft's voltage regulator to be sure it's providing the correct charging voltage. Refer to the aircraft manufacturer's manual and the Gill service manual for recommended voltage regulator settings. If the voltage is too low, the battery will not be kept fully charged. If the voltage is too high, excessive gassing will occur, resulting in more rapid loss of water and shortened battery life. To maximize the life and performance built into a Gill battery, check the battery periodically for its state of charge, electrolyte level, and general condition. If aircraft service consists largely of short flights and frequent engine starts, check the battery more often. Slower spooling speed and higher starting temperatures may be an indication that the battery could require recharging or replacement. It may also be the result of poor battery connections or other aircraft component problems. Recharge the battery whenever specific gravity falls below 1260 or if the aircraft has been out of service for more than 30 days. An unused battery will self-discharge at a rate of approximately 1 point of specific gravity every 24 hours. A dirty battery can self-discharge at 3 times that rate. Here are a few rules for adding water to the battery and for servicing the sump jar. When you add water to the battery, fill each cell just to the bottom of the split ring while the battery is warm and in a good state of charge. For example, check the battery and add water just after a bench charge or following a flight of an hour and a half or so. Do not add water if the battery is cold or in a low state of charge unless electrolyte is lower than a 1/4 inch above the plates. A higher level in this state may cause the battery to overflow as the electrolyte expands during a long flight. Check and clean the sump jar every 200 hours of operation or if there has been an overflow. If the battery needs to be recharged, it should be removed from the aircraft and serviced in a designated area. Charging or cleaning the battery in the aircraft is not recommended. Check and record the specific gravity of each cell. If necessary, add enough water to cover the separators. Then charge the battery until the specific gravity stabilizes with all cells reading between 1260 and 1300 for 3 consecutive hours. Add only distilled or demineralized water. Never add electrolyte unless it has been lost by spillage or diluted by addition of excess water. Charge the battery with all vent caps securely installed. If the specific gravity for any cell will not come up to its recommended operating range, the battery may be badly sulfated as a result of being unused or may have been completely discharged. Continue charging at 10% of the 1-hour discharge rate until the specific gravity reaches its normal operating range. This procedure could require 48 to 72 hours. Adjust electrolyte to the bottom of the split ring, being careful not to overfill the cell. Every Gill battery is rated at the 30-minute emergency capacity specification and is considered serviceable to 80% of that rating. For example, a 24-volt battery must provide its rated current for at least 24 minutes to the minimum cutoff voltage of 1.75 volts per cell, that is 21 volts. Remember that the battery must be recharged following the test. Many turbine aircraft have been converted from NiCad to GIL lead-acid batteries. If you are to perform a conversion, ask your GIL distributor for the proper STC, which will include a kit containing the parts and accessories necessary for proper installation. The STC kit includes instructions for deactivating heat sensing or current monitoring equipment required for NiCad batteries. This equipment is not necessary for lead-acid batteries. Teledyne has obtained STCs for most popular turbine-powered aircraft. Your GIL dealer can give you a current list of available STC kits. If an STC has not been developed for the aircraft you're working on, perform installation using FAA Field Approval Form 337. Follow the guidelines given in FAA Advisory Circular 43.13, covering lead-acid battery installations. No matter what battery procedure you are performing, refer to the GIL Service Manual for supplementary or detailed instruction. Following the simple procedures we have just reviewed and which are detailed in the service manual will help your GIL battery operate at peak performance. Remember that the key to maximum power and long life is keeping your battery at or near full charge at all times.
Real men and women. All right, we are going to, in a minute, take a short break. Just for the fun of it, I brought my hydrometer back in here, and I have just water, because I washed it all out like we're supposed to, right? And, ooh, I got one ball stuck at the top. My battery's kind of charged. Well, probably not. It's probably just holding on to a bubble. So, make sure you do the little tappity-tap thing, because if there's a bubble holding on to it. So obviously, now my battery's not charged, because I'm 100% water, right? So, you're welcome to play around with these in here. Hopefully everybody rinsed them, but otherwise we will move those out there. Well, I'll bring them out there shortly, but if you want to test it on not acid a couple times just to see what you're doing, you're welcome to do that. I did want to point out, we do have the emergency shower right outside the bathrooms, right? Did you guys go over that with safety class? All right. Hopefully nobody has to use that this year, but I mean, when we're working with batteries, if something were to happen and it's still on you, that's probably the first place I'd go is go rinse off. Yeah.
Do you rinse those hydrometers with just like tap water, or?
I have to stop the recording. If you're working in a shop and out there we have, it's a gallon of distilled water right there. Probably on real aircraft, you'd be like, you know what, let's rinse it with distill. The reality is the small amount of minerals that you're gonna get on it, especially we're not in real aircraft, we'll just use tap water. So for you guys, tap water's fine, rinse them out, we'll be good. Great question. Probably not gonna, even if you did it in a shop, not gonna matter if you rinse it with tap water once. Do it 100 times, well, it might be an issue, but yeah. Rinsing, we'll leave it at that. Good question, I like the way you're thinking. Anything you guys picked up from the video that stuck out? I had two that I was like, oh, that's a good point. No? Just a boring video? One of them was, I thought it was interesting, they said self-discharge, so say like 6741 Echo, I'm hoping to take out to the Tigers game Monday afternoon, because Tigers are really doing great. You guys are stuck in school, but I've got cousins that are like, can you fly us to Cleveland? I'm like, you buy me a ticket. So anyway, the airplane's out they said the battery will often self-discharge at 1 point, did they say a day or an hour?
Day.
At one point a day, yeah. It's not gonna go from 1.267 to 0.267, right? I noticed they converted their decimals over like the hundredths, which is interesting because it's a specific gravity comparing the density to the density of water, right? So, I don't know, you don't get a kilo specific gravity, but they just get used to, instead of saying decimal all the time, they're saying 1,267, they just eliminate the decimal. So, park that thing for 365 days, and you basically go from a 1.3 fully charged to a 1.0, which is water. So just in my head, I'm like, oh, that's interesting. So it can park for about a year, and I'm fully discharged. I don't know if the math lines up, but that's where the math would line up if you're a math guy kind of doing it in your head.
What's the reason you can't charge your battery?
In the aircraft, mostly what they're gonna be worried about is silly stuff like the leads falling off, hitting the aircraft. Also, if something's wrong with the battery, or say you're adding fluid and you do it wrong, and now we charge it and it warms up and it overflows, we do not wanna corrode our aluminum aircraft. So it's actually, if something goes wrong, silly stuff, because when we're operating the aircraft, we charge it in there all the time. But yeah, it's just, we start taking those caps out, so to check our fluid level, or, not, well, fluid level, yes, but to check the charge, we have to take the vent caps off, right? Man, you mess up with a little squirt, are you really gonna clean it up good? Well, you better, but that's the idea, is all the things that could go wrong, spilling acid, we don't want them to go wrong in the aircraft, we want them to go wrong in our lab, where it's super easy to clean it up. Good question, though. All right, the last piece, we didn't do the NICAD video yet, but for, I'm gonna say decades, NICAD was kind of like, this is where we're going, the new batteries. You notice they said turbines are converting back to lead acid. The idea was, when they were making those turbine aircraft, the NICADs are a little bit more, I'm gonna use the word power dense. People were switching over to NICAD. The issue is, with the different issues of voltage memory, thermal runaway, stuff like that, the thermal runaway is the big one. There's a lot of turbine aircraft manufacturers now that say, hey, if you got a NICAD battery, we're gonna have you monitor the temperature of the battery, so we know if you're getting thermal runaway, and we're gonna have you monitor the amperage with a couple different ways, and that all costs money, it adds weight, and it's expensive. So people with turbines are like, well, phooey to this, I'm going back to lead acid. So, which is better? Well, it depends who you are. A lot of it depends on how long you store it. NICADs don't like, well, there's storage issues. NICADs don't like to be stored without use, and anyway, so which battery's better? Well, it all depends on how you're using it. Okay, it is break. I'm gonna say we'll call it a 10-minute break, but on the break, let's all walk out together and I'll point out the batteries that are available and where stuff is, and then you can take your little break. So somebody will grab, that was dangerous. Grab the door for me, we'll head out there.
Yeah, sure. All right. One in the front, one in the pillowcase front.
happen to do a control cable? Or you owe it to
I
me?
was gonna do that today. If we own that. If someone else did too, I'll take theirs.
Does that help you or hurt you?
Probably heard me. I'll just talk.
Hurt you. What, maybe when you go press at some point.
Yeah.
servicing that same question, right? Like, how do I know if it's good or bad? Everything's sealed in a can. Then we get pretty excited about knowing if it's good or not.
You puncture the can, you have a bad day.
Yeah. I mean, go on a flight all by itself and they're like, no lithium batteries, right? Doesn't even let you, what if something were to happen?
Right.
So they get pretty excited. They like to say the 787, I don't even know which one that is, but big
Some
one, right?
big plane.
The 787 has two great big honking lithium batteries, so that's what it came out of the factory with. So they like to talk about that, because like, the future's lithium, and we're going to it, but, they haven't all gone to it. So, more common is, you know, we have APUs you'll learn about, we got a little turbine that's making power. So more common is instead of these honking big batteries, we'll just get an APU to run and provide the power. So use something to start our APU in the aircraft, or maybe a small battery to start an APU.
Lead acid to start the
Yeah.
APU, the APU to
And
start
then the APU essentially acts as, you don't need a battery anymore, because it can adjust.
It's an expensive pony motor.
I believe safety-wise, that's cheaper than having honking lithium ion, or hauling around a bunch of lead. They just say, we'll make our own power. Or they'll take it off the turbine of the engine that's running, right? They'll say, you know what, instead of a big battery, some aircraft, they'll just ground start off the car. Say, ground start.
Are there aircraft that are only ground start?
There are, I can't name them, but, yeah. Trying to think of which ones. Can't, I'm not an aircraft, it sounds bad, I'm not an aircraft guy that's got all that stuff memorized. But yeah, there's some of them where they're just gonna do ground start. Whether it's electric or, a lot of times usually it's gonna actually be a pneumatic that we'll learn about. So they'll just pump pressurized air in and start it off that. Okay, I gotta figure out, I probably should have done this earlier, how to play the DVD player. Come on, open it. Open sesame, there it is. Okay, DVD, loading. Alright, next video is more of the same, but NICAD. I apologize that it's 20 minutes long, or maybe you enjoy it. Really interesting to see NICAD. I don't talk too much about, but the part to really pay attention to is how each individual cell in a NICAD battery is its own individual cell. So they're going to go through the manufacturing process, and basically they're going to make all the individual cells. It's not like those lead ones where you can kind of slosh the fluid around, they're kind of all connected. It's individual cells, and then they'll wire them all in series or parallel or whatever they got to do to make the battery they want. Is it playing?
There's absolutely no doubt that airplanes are becoming more electrical. How familiar are you with electrical theory? Precision Airmotive offers this aircraft electrical system troubleshooting video presentation as an alternative to earning a bachelor's degree in electrical.
There we go. Sorry, wrong one. That might be later in the year. We've really progressed in aviation. We're going to show you 30-year-old videos. It's still appropriate. Part of it is you're working on 70-year-old aircraft. So, all right, try that.
There's a lot that goes through a pilot's mind, but one thing he shouldn't have to worry about is the condition of his battery. Today, the Marathon nickel-cadmium battery is the most widely used source of startup and emergency power for modern aircraft. From helicopters to fighters, from airlines to corporate jets, a Marathon battery is standard equipment. Marathon, the battery with staying power. We were the first to build a nickel-cadmium battery for aircraft, and we supplied the United States Air Force Strategic Air Command way back in 1958. And today, here in this 200,000 square foot facility, we design, develop, and manufacture batteries to exceed the needs of today's and tomorrow's aircraft. Research and development, making improvements for tomorrow's power sources. Engineering, where we custom design batteries to client specifications. Manufacturing, hundreds of different batteries and accessories. And just as the heart of a battery is the single cell, the heart of our company is our employees, each an experienced professional in his field, producing products to exacting specifications. The Marathon nickel-cadmium aircraft battery has at its core the sintered plate made from carbonyl nickel. Carbonyl nickel is sintered onto a grid as it moves through a reducing atmosphere under high temperature. This process creates a plaque, highly porous like a sponge, yet highly conductive. Each plaque has a surface area equal to several hundred solid plates the same size. The plaque is then coined, which further strengthens the plate. Plaques are now ready for chemical processing, where they become either positive or negative. If a plaque is impregnated with nickel salts, it becomes positive, while impregnating with cadmium salts will create a negative plate. After washing and drying, the plaques are cut into the individual plates. The plates are cut with round corners rather than square corners, which decreases the possibility of shorting. Tabs are then welded into each plate. Marathon takes the extra step of double tabbing each plate. This means a stronger electromechanical joint and lower resistance. Stacking is next. Continuous 3-layered strips of special separator materials are folded alternately between the positive and negative plates. The separator materials have two seemingly contradictory functions. On one hand, they keep the oxygen formed at the positive plate from combining with the cadmium at the negative plate. But they also have to permit free movement of ions in the electrolyte between the positive and negative plates. Marathon's standard product has a triple layer of polypropylene cloth, cell guard, and polypropylene. The cell guard material acts as a gas barrier to keep oxygen generated at the positive from contacting and thereby discharging the negative. We use cell guard on all of our superpower low impedance batteries. After many years of field testing, it's proven to have longer life, superior durability, low internal resistance, and better low temperature performance. After stacking, the tabs are carefully combed. This operation eliminates stress at the tab to plate weld area. Terminals are now welded to the tabs. The plates are kept in a fixture to maintain core uniformity. That's another Marathon trademark. At every step, there is a close attention to maintaining exact tolerances, and then inspection stations to make doubly sure. The cover assembly is attached and each cell is individually inspected prior to sealing. The case and cover interface is heated and a one-piece homogeneous bond is formed. Then each cell is pressure checked 100% for possible leaks before it can leave the factory. The cells are then filled with electrolyte. Our vacuum process ensures that electrolyte saturates every pore of the plates. The cells are then grouped together and electrically tested. The cells are now working electrical systems, ready to be assembled into another Marathon battery or sold as individual cells. Our battery cans receive the same careful treatment. They're usually made of cold-rolled or stainless steel and heat-coated with an epoxy powder in this exclusive dry painting process, resulting in a durable finish which is impervious to cell electrolytes and has excellent electrical insulation properties. Next, cells are installed into the battery cans along with specified sensor assemblies. The intercell connectors are torqued and the new battery is subjected to a charge and high-rate discharge. Every Marathon battery is subjected to a discharge test simulating the load that it will experience when it's placed in service. Marathon's quality control department pulls samples from the line and keeps a record on each battery, showing the various tests performed and the results. We take our responsibility as a world-class supplier of aircraft batteries very seriously, and we stand behind every unit we manufacture. The Marathon nickel-cadmium battery is ready for you. Marathon nickel-cadmium batteries have a well-founded reputation for being dependable, low-maintenance power sources. But you must still remember that the battery is an electrochemical system which must be periodically checked and maintained in order to deliver long life and dependable service. There are two main functions of a battery in an aircraft. It must start the aircraft, and it must have reserve power in case of in-flight power failures. To assure good battery performance, Marathon provides a manual with maintenance procedures and service details. However, the only true guide to the frequency of service is the service log. The log is the personal history of each battery. Not only does the log show how the battery has been serviced, but it also shows when the battery needs to be checked again. Also, proper records are required for a warranty to be validated, so the importance of record keeping cannot be overestimated. The first step in battery service is to make a visual examination of the battery and can. Look for damage to the can, such as dents from rough treatment. Next, take off the battery cover and check the intercell connectors for discoloration. And now is also a good time to check for proper torquing of the connectors. Next, check the mating connector for discoloration, oxidation, and evidence of wear, which could cause a poor connection that would create high resistance. Go, no-go inspection gauges and service bulletins are available from the connector manufacturer for the purpose of checking wear on the aircraft quick disconnect. Now clean off the tops of the cells using a nylon brush or compressed air, free from oil or water. If the battery requires extensive cleaning with water, see the Marathon Battery Maintenance Manual for the exact procedure. The next major procedure is the electrical leak check. In this procedure, you will be looking for current leakage between terminals or connectors and the battery can. Current leakage can be caused by electrolyte spewage resulting from overfill or high voltage regulator setting. Remember to use the current setting only. Do not use the voltage reading as a criteria. A reading of more than 50 milliamps between the negative or positive terminal and the can is excessive leakage and will require you to disassemble and clean the battery more thoroughly than the routine brush cleaning. The maintenance manual gives the exact procedure for tracing down the source of current leakage. Next, we will check the electrolyte level. But before you do, put the battery on top charge using a constant current charger such as the Marathon PCA 231 charger analyzer. The electrolyte level will vary depending on the state of charge. The only way to obtain an accurate electrolyte level is to charge the battery until it is gassing freely and then adjust the electrolyte level. Again, the exact procedure is outlined in the maintenance manual. It is very important to use distilled, deionized, or demineralized water for adjusting the electrolyte level. The chemicals and minerals in tap water can destroy the electrochemical balance within the battery and will shorten its service life. Never add potassium hydroxide. Too low an electrolyte level will result in diminished capacity and battery life. However, do not overfill. Putting in too much water can cause electrolyte spewage. The next service step is the capacity test. One problem that frequently occurs with nickel-cadmium batteries is a temporary loss of capacity. Reconditioning is necessary to restore the battery to full capacity. That is, its ability to deliver its full amount of electrical energy. Batteries lose capacity for many reasons. For example, some charging systems do not restore enough electrical energy to the cells because of voltage regulator settings, ambient temperatures, or frequent starts. In any case, an imbalance develops between the capacity of the individual cells, resulting in a temporary loss of battery capacity. The only true way to find and correct this condition is to discharge the battery at a fixed rate for a specified period of time to a predetermined voltage cutoff. The time it takes for a battery to run down to its cutoff voltage, which is 1 volt per cell, is the true measure of a battery's capacity. There are tables in the maintenance manual which show discharge rates and acceptable capacity for every Marathon battery. Batteries may be tested using a constant current charger such as Marathon's PCA 231 charger analyzer. This charger allows you to select rates of charge and discharge and is programmable to perform all reconditioning procedures. The capacity test is done regularly to every battery as a routine check of its capacity. When each cell reaches 1 volt, note the time. If the capacity is more than 85% of what is specified in the manual for the battery that you are testing, then the capacity is considered to be acceptable, and you may proceed with the recharge. If the battery has less than 85% of the rated capacity, the discharge will continue and the cell should be shorted out as outlined in the maintenance manual. This is called deep cycling. Deep cycling means that the battery is being completely discharged. In order to do this, continue the discharge until the individual cell voltage drops below 0.5 volts. Then short out the cells completely. The exact procedure is outlined in detail in the maintenance manual. After deep cycling, charging and top charging the battery is required. In this step, the battery is charged to replace 100% of its theoretical capacity and then overcharged or top charged. Moderate overcharging will not harm the battery, and in fact, it's necessary. Because of a characteristic of nickel-cadmium batteries, they actually must have more electrical energy restored than is removed due to charge inefficiencies. Charge and top charge rates are listed in the maintenance manual. Total charge will only take 4 hours. The next step to be performed on the battery is the end of charge voltage tests. The end of charge voltage test will tell you the condition of the gas barrier in each cell, and as such, it is one of the most important tests you will perform on the battery. This voltage test is performed during the final minutes of the overcharge. Check the voltage of each cell, and remember, in order to perform the test correctly, the battery must be on charge and the ampere hour input must have exceeded the ampere hours removed. The minimum acceptable voltage is 1.55 volts per cell. The maximum is 1.75 volts per cell. If any cell fails to make the minimum, continue the overcharge for 1 more hour. If necessary, reset the charger to allow the continuation of the overcharge. If after this hour any cell fails to make 1.55 volts or achieves 1.55 and then falls below 1.50 volts, then that cell probably has a defective gas barrier and must be removed from the battery. If you do have to replace a cell, be sure to mark it on the record. Remember, when more than 5 cells are replaced from any one battery, that battery should be removed from service. The chances are good that other cells within the battery have also sustained some damage. What happens if a battery with defective separator material is allowed to remain in service in the aircraft? The greatest danger is thermal runaway. This is also referred to as vicious cycling. Thermal runaway is a chain reaction that is most likely to occur with the kind of constant voltage, high current charger found on aircraft. Under normal conditions, as the battery voltage rises to the preset voltage regulator value, the current should level off to a very low value. However, if the battery becomes warm, heat may be generated faster than it can be dissipated. For example, damage to the gas barrier in the cell will cause a slight rise in cell or battery temperature. The heat rise causes the internal resistance of the battery to go down. When resistance goes down more than current flows in, which makes the temperature rise even more, a vicious cycle is begun. More current is used and more heat is generated, causing a lowered gassing potential and lowered resistance until the cell in the battery could be severely damaged. In the shop where you're attending the battery, noticing heat buildup is a simple matter. But in the aircraft, the only direct warning comes from either the temperature sensor attached to the battery or a rise in current flow as shown by the aircraft ammeter. Therefore, it is extremely important to be sure that the temperature sensor is working correctly. Thermal runaway can be stopped immediately by removing the battery from the charging source. The end of charge voltage test is the only test capable of finding gas barrier breakdown, which is the main cause of thermal runaway. Remember, a battery may need to be deep cycled up to 3 times in order to bring it up to the required capacity. But if a cell once fails the end of charge voltage test, that cell should be replaced. To replace a cell, follow the procedure outlined in the maintenance manual. Once the battery has passed these major tests, you will need to recheck the electrolyte level, adjust the torque on the intercell connectors, and recheck the battery for current leakage. Once the battery has passed all these tests, you can be confident that it will provide excellent starting and standby power. At Marathon, we have a saying about battery maintenance. You get out of the battery what you put into it. Most battery failures occur within 15 hours of being serviced, so it's important to everyone that you follow our recommended maintenance procedures. And there is a definite correlation between long high temperature starts, usually caused by a weak or defective battery, and shortened engine life. Marathon stands behind its batteries and you. We make hundreds of different kinds of aircraft batteries, so if there's a problem in application, design, or maintenance, the chances are that we've solved it before. Our experience includes accessories and monitoring equipment, temperature sensors and heater blankets, as well as the PCA 231 charger analyzer. To make your battery servicing task easier, we packaged all the special tools into a convenient maintenance kit. To keep pace with the greater power requirements of tomorrow's aircraft, we've introduced a new generation, the Superpower. Our experience includes not only our aircraft batteries, but special purpose sealed cells. And Marathon offers the kind of service unprecedented in the industry. Our service and distribution centers extend around the world. If you want the most reliable start in the industry, fly with Marathon.
But it depends on who you are. So one thing that they said I want to touch on was if you view the box of a NiCad as being, it's a metal, it's a ground piece, if you will, and all the individual cells on the inside, they're not grounded. Is that a fair way to put it? You got a plus, you got a minus inside. So what they did is they put an amp meter between the positive terminal and just the shell of the box. And in a perfect world, you have no amps, right? Because it's insulated in here. There's no way for current to flow from the positive to the box and get back to the negative. But let's say you had electrolyte spillage or damage or something so that the shell of the box got to where it was connecting, there was a path for electrons. Then our amp meter might read some sort of amperage from our positive to the shell of the box, from the shell of the box back to the negative terminal. So that's what they're talking about. You'll probably not do that, but it was a good opportunity to kind of look at and say, what do you mean you're checking with an amp meter, not a voltmeter? Is instead of measuring the voltage, they're saying, well, depends on how sensitive your voltmeter is. If there was kind of a tiny little bit of leakage with a crazy sensitive voltmeter that's not going to have amp flow through it, you might pick it up. So until it's up to a certain level, we're going to check it with an amp meter instead. So that's where they were going with that one. Kind of interesting. piece of info. Then the last piece is on a NiCad, you can replace individual cells they talked about. That's kind of cool, right? They made mention, the video said you can't replace more than, I think, 5 in each battery. I don't believe that becomes a question, but every once in a while you'll see, hey, could I just replace like half the cells, replace all the cells? And they go, well, you had 5 fail, something, you must have done something wrong. So we're just gonna replace the whole thing. All right, that's all I got for today. Lab time, you don't have much time. I'm gonna look through the PowerPoints. I think you'll end up with more lab than lecture kind of for the rest of the cycle here. So if you're pacing yourself out and seeing where you're at, that is where we're at. So sign up for a crew. If you're not signed up by Monday, I'll sign you up myself. Dismiss. I'm gonna take a little 10-minute break that's not really a break. And I'm gonna